I was out on a site, and it was to do with pressure testing piping systems or pumps with air. And you made a comment that it's not a good idea, and we're going to go through that right now, right?
Yes. So if you look at it, so there's two ways that you can pressure test a piping system.
And we're
One is
talking
a
about
hydrostat.
we're talking about hydronics here, right? We're not talking about
Well,
refrigeration or
well, technically, and I'll address that here in just a minute,
okay.
because it's all covered by ASME. Okay, so let's talk about. There's two methods of testing piping. First of all, one is hydrostatic, which of course applies to any piping system that conveys water.
Can you
Or
explain
glycol.
hydrostatic? Can you explain
Hydrostatic
hydrostatic?
means that you're going to fill the piping system with water, completely get rid of all the air, and then increase the pressure above the design pressure of the piping system, whatever the design operating pressure is. Okay, so that's a hydrostatic test. The other type is a pneumatic pressure test, where you're going to use compressed air. Now, or other compressed gases, okay, nitrogen or carbon dioxide or something like that. Understand that all piping systems are covered by one of four ASME codes. And ASME is the American Society of Mechanical Engineers.
Can I stop you there for a sec, Tony?
Sure.
Your mic's rubbing on your shirt or something like that.
Okay.
So
Is that better?
I don't know if it was the cable that was
I think it was hitting the cable.
Yeah, the cable was rubbing against your shirt. It's okay. So now I think it's better now.
Okay. So
okay, go on.
Piping systems are covered by the ASME pressure piping code. And the pressure piping code is ASME B31. There are four subsections to B31 that cover piping systems, depending on what the piping system is. Okay, B31.1 is power piping, and that is steam piping above 15 psig. Okay, 31.3 is process piping, which is also steam piping above 15 psig, but it's piping specifically in the process world, because it also covers oils and other fluids that you may find in the process world that you don't necessarily have in the HVAC or normal sector. And there's a whole bunch of rules about static loading and thermal expansion and all kinds of other stuff that talk about how much tension or stress load you can put on fittings. To give you an idea, okay, in a piping system, in a steam piping system for a power boiler for anything above 15 pounds, I cannot, by the boiler manufacturers, I cannot impart any stress load on the outlet nozzle of the boiler, which means that as the piping heats up and expands, I can't create any dynamic forces that twist or turn that boiler nozzle. As an example, if I have a 175 psig steam boiler and I bring it up to temperature, if I don't have the piping properly restrained and designed to move correctly, I can impart a stress load of in excess of 50,000 pounds on the nozzle of the boiler. So basically, I'm trying to twist that nozzle or make it move in directions that it's not supposed to move. So I'm putting all kinds of stress loads on it, which leads to failure. So beyond that stuff, there's another section of the ASME B31 code that's 31.5, which talks about refrigeration piping and heat transfer components, specifically to the refrigeration industry. And pressure testing is detailed in that section as well. The other one, and the very last one, is B31.9, and that's building services piping. Building services piping is what covers literally all of the HVAC world once you move beyond, that steam distribution system in a high pressure piping system. So everything we deal with for normal hydronics is building services piping. But it also covers stuff like high purity piping. So I know a lot of your folks don't necessarily do high purity piping, but in the semiconductor industry or the pharmaceutical industry, maybe doing stainless steel.
When you say high purity piping, you talking about like an oxygen line or something like that?
Yes, that is covered in that. But high purity piping could also be high purity water. So for pharmaceutical production or breweries, anything like that. So You can have high purity piping in a animal research lab. So all the drinking water that goes to the animals' pens, they don't want to give the animals that are drinking water anything that could alter what they might be studying. So if
Gotcha.
they're studying nutrition, they want to make sure there's nothing in the water that's going to mess with what they're feeding them.
I gotcha. Okay.
So you kind of have to understand that's where this all comes from, is what is defined in those 4 code sections. So a lot of engineers will specify, a pressure test that is 1.5 times the design working pressure. Now,
All right.
keep in mind, the design working pressure and the maximum allowable pressure are 2 different things. Okay. The design working pressure is the pressure the system's going to operate at under normal conditions. It's not if it's 100, say it's 150 PSI piping system with, 150 PSI rated flanges and all that. That's not necessarily the design working pressure. That's the design pressure limit. That's the design maximum pressure. So ASME talks about the design working pressure. The design working pressure is whatever pressure you're going to operate. So if it's 15 PSI or 20 PSI or 50 PSI, SME goes on to say that the pressure that the piping system should be tested at 1.5 times the design working pressure. Okay. So let's say that, we're looking at this piping system and it's a 50-pound system. That means I should test at 75 PSIG. Okay. Now, if I test, actually, let's say it's 100 pounds, because that'll lead into my examples here. If I test with water, I'm going to raise the pressure to 150 PSIG. Fill the entire system with water, raise the pressure, use a hydrostatic test pump, and pressurize it and push the pressure up. Now, mind you, water's not compressible, right? So what that means is that it doesn't take a whole lot additional volume to increase the pressure to 150 PSIG. One of the other advantages, and I guess we'll talk about testing with air. So now let's say I take that same piping system and I fill the entire system with air, compressed air. It takes an awful lot of compressed air. There's an awful lot of volume of air in that system if I pressurize it with compressed air. That's also a tremendous amount of stored energy. Okay. So if I think about stored energy and I'm pushing all this air into the system, that stored energy, this number will scare you. Okay? If I have 500 feet of 6-inch pipe, now think about it. Think about a building. 500 feet of 6-inch pipe really isn't that much pipe, right?
If you're talking about a high-rise building, it doesn't.
Yeah, I
You
mean,
get to that
there's a
pretty
lot of buildings
quickly.
that I can bury 500 feet of pipe in that building really quickly. That is equal to 5 pounds of TNT, 5 pounds of dynamite in explosive force. That's the energy equivalency that's contained in that 500 feet of 6-inch pipe.
And that's with air pressurization.
That's with air. Okay. Yeah. Because the amount of stored energy that's there. Think about it. If that air gets out, how much volume is there? There's an awful lot of volume when that gets out. And there have been numerous examples. If you go out on the web and you start searching, there's all kinds of incidents where they've used compressed air to test piping systems. And what ends up happening is that pipelines explode, and they explode violently. They create shrapnel. One of the downsides to testing with air, okay, I pressurize a system and I pressurize it to 100 pounds, 150 pounds. I can't see the leaks. I don't know where they're at.
Yeah.
I mean, I pressurize it and I valve everything off and I let it sit. I mean, it's no different than testing a refrigeration system with nitrogen, right? You pressurize it. Now you got to look for the leaks.
Yeah.
Well,
hopefully you can hear them, but otherwise,
hopefully you can hear them, but not always.
Yeah. True.
Well, in a piping system, a lot of times that piping's buried in walls. It's hidden in places you can't see it. It's 30 feet in the air. So finding the leaks is a challenge. The other problem is, I talked about the explosive force and what happens, what that is equal to in explosive force. Really good example. Here in Columbus, where I live, there's a pretty good sized mechanical contractor Their guys were out testing a piping system, conventional hydronic system, nothing oddball, nothing weird. There was I think a 3 or 4 inch blind flange mounted on the end on a fitting, and it was bolted on, and the nuts and bolts were there, and the gasket was there, and they had it up, and they pressurized it, started bringing it up, and they were in a mechanical room, and mechanical rooms are noisy, they're not quiet, and they got the pressure up, and I want to say the pressure was at 50 or 60 pounds. And whoever was running the project walked over to this blind flange and noticed that the bolts weren't tight, because he heard some leak, heard some air hissing out. And he goes to get on this thing to tighten it down, and the nuts were only on the bolts probably half a turn. That's how loose they were. They really weren't where they should have been, or at least most of them weren't.
Okay. Yeah.
And he went to touch this thing with it still pressurized, and it came loose violently. The cap came off, or the blind flange came off, and my guess is it sheared the one bolt that may have been tightened down a little bit, but it came off and it flew, and he was fairly close to it. It flew and hit him in the face. Did quite a bit of damage. Number of surgeries later. He is permanently disabled. He was 40 years old 35, 40 years old when this happened. This was about 10 years ago, maybe 15, but it almost killed him. It was purely by the grace of God and some really good emergency room physicians that it kept him from dying. And that was just from a flange coming off and hitting him in the face. Now, we all wear safety glasses, and we wear hard hats, and we wear gloves and all this other PPE. That flange coming off at 100 and some odd miles an hour, I don't care what PPE you got on. When it hits you square in the face, the safety glasses aren't going to help you any.
Yeah.
They're going to get embedded.
Yeah,
and
they might even get cracked and shrapnel of the glasses in your eyeball too, right?
Right. And so that's the thing. You have to understand, you've been around long enough. I'm sure you've picked up a 3-inch pipe flange. They're not exactly the light. I mean, they're not super heavy, but I wouldn't want to drop one on my foot, let alone get hit in the face with one at 100 miles an hour.
Yeah.
And so we have to understand that this is the reason we don't want to use compressed air to test piping systems. Now, yes, there are instances that you have to use compressed air. Okay.
Well, I mean, let's talk about the refrigeration side for a minute, and then we can move back to your hydronic piping. I mean, we don't have a choice but to use compressed gas. We don't want to use air. I mean, because air contains moisture, so we want to use a dry gas, and that's why we use nitrogen. But we don't have a choice, and it always scares me when I'm pressurizing a new system because some of these manufacturers, they want to test it to 600 psi. It always scares me. Like, what if that high pressure control on that thing goes flying off the thing because the factory or someone didn't braze it properly or tighten it down properly because it's got threads on it or something like that. It always scares me working around systems that run that high pressure or pressurizing up to that, because something might let go, right? And like you said, it doesn't. I mean, let's say somebody forgot to put a Schrader cap in, right?
Oh yeah.
And then you hear a bit of a hissing sound, and you go to take that cap off, and then it's tight. You're like, that's weird. Why is it so tight? And you finally get the cap off, and it's blowing out because somebody forgot to put, which has happened to me before, right? And I mean, if you're not educated enough on, you could be standing right in front of the thing, loosening it right in front of your face, and the cap can go flying and hit you in the eyeball. So there's so many things that you got to be wary about when you're pressure testing. But that's always scared me on the refrigeration side. And here's the other one I want to throw out too, just before you move on, is that guys take their recovery cylinders when it's cold and they dunk them and I've seen it happen in a bath of hot water. Well, there's a danger to that too, because that bath of hot water is going to engorge the tank, and you don't know what the pressure of the tank is when you do that. You could shock it, and that pressure could go up really, really, really quick, and you could have something happen to that tank, And I mean, they've got relief valves. The relief valve could blow if it's faulty. The tank could explode. There's all kinds. I've seen copper pipe explode from refrigerant pressure too high. That was a mistake of me and my coworker, and I've told the story before. But I've seen copper pipe burst in half, and basically it put us on our back. I don't know how we survived and didn't go blind from it, to be honest with you. But that's why I don't like when guys take recovery cylinders and put them into a bath of hot water, especially if they don't have a gauge on monitoring what the pressure is in that tank. So,
Right.
so many different things could happen with vapor pressurization, right?
Well, and you bring up a good point with the whole stick the refrigerant recovery cylinder, or even a brand new refrigerant cylinder, in a bucket of hot water to get it to boil off, to get the pressure to come up so you can charge your system. Well,
Yeah.
the problem with it, and in today's world with liquid charging, because of the new refrigerants, it's not quite as bad as it used to be when we had, R12 and R22 and had to charge in vapor. But the fire service actually has a name for that condition that happens when you have a liquid that rapidly vaporizes and violently leaves the cylinder, and it's called BLEVE. It's boiling liquid expanding vapor explosion. Because if you think about it, you take that cylinder and let's say it's got, it's 50% full of liquid, right? And you take that cylinder and you stick it in a bucket of hot water. Now, the problem is that, think about where the boiling point of refrigerant is. What's it going to do? Refrigerant's designed for one, refrigerant is one, its chemical properties, it's specifically designed to transfer heat, right? And it's going to boil rapidly at that elevated temperature. We know that 410A has got an operating head pressure, well north of 400 pounds, right? So if you think about it, you stick that cylinder in a bucket of hot water, how quick is that 410A going to boil off?
Yes.
It's going to boil off really quickly, and you're going to get really high pressures really quickly, and you may very well exceed the pressure limit of that recovery cylinder.
Yes. And that's why I tell guys not to do it. And they're like, well,
Right.
I've never had a problem. Well, I'm like, you've never had a problem until you do. So
right.
I'm just telling you what I've learned and what I've seen and what I've learned from other technicians. I mean, it might not happen often, but when it does happen, like, be prepared, because it's not going to be pretty if
no,
something
all it
happens
takes is
one
time,
Yeah.
and it will change your opinion very quickly. When we look at a piping system, and you talk about pressure testing refrigeration systems with dry nitrogen, and yes, we want to pressure test to 500-600 psig, because that's where this thing's going to operate, right? If you got an operating head pressure of 5, with these 410A systems, and if you got an operating head pressure of 500 pounds, I want to test the piping system at greater than 500 pounds. So what you have to look at is, first of all, what are the pressure limits of the different components in the system? Okay, most evaporator coil is 150, 200 psig, right? So you got to think about the piping system and how you're going to isolate it to test only the parts that are designed for 600 psig to be tested at that. That's one thing.
Unless it's a heat pump, I'll just throw that out there, because the
right.
heat pump system is designed for both sides to take that maximum pressure. So
right.
You're good there. But you do bring up a good point, is that you have to look. And I just talked to another guy, AC service tech, about this. If you're pressurizing something that was R22 based, your pressure limits for testing are going to be much lower. So you have to pay attention to what the design pressure is and pressure test to that. You don't want to be going higher than it, right?
Right. Because typical R22 evaporator coil was, if I remember correctly, was like 150 psig maximum.
It was something along those lines. Yeah.
Yeah. And I've been away from that for a little while. I don't remember exactly. But the thing you have to understand when you're pressure testing that system, and it goes back to everything you were talking about with, a Schrader valve not being under a cap, and you go to try to take the cap off and you're like, ooh, wait a minute, something wrong here. Well, what you really should be doing is pressure testing in increments. Don't just hook your nitrogen cylinder up and jack that thing up to 600 pounds in one fell swoop.
100%. Yeah.
Take it up to 25 pounds, take it up to 50 pounds, start checking stuff. Leak soap is my friend. I don't care if I use a gallon of leak soap to check a system. Guess what? Leak soap is a whole lot cheaper and a whole lot safer than me getting blasted in the face with a fitting.
And you save on night. Like, if you go up to 25 or 50 and you hear a leak or it starts dropping, you're like, okay, I got a leak at 50 psi. I don't need to waste my resource of my nitrogen tank and go all the way up to 600 to know there's a leak. So yeah, it
Yeah.
makes a whole lot of sense. Yeah.
Well, especially if you're on a roof and you had to drag that nitrogen cylinder from your truck all the way up onto the roof with you. You don't want to take more than
Yeah.
one cylinder up there if you don't have to, because they're
Exactly.
heavy. I'm glad I don't have to do that anymore, because nitrogen cylinders aren't exactly the lightest thing to carry.
No.
Um,
Nope.
and there's no easy way to get them on the roof. I don't care how you tie them off with a rope and pull them up there. It's not fun.
No, it's not.
And understand that if you if you test, and you test in increments, and you find that small leak, you get that leak fixed, then you move on. I know we've migrated to press fittings on a lot of refrigeration systems, getting away from brazing. The downside to press fittings is, if you forget to press it and you don't pay attention, and you pressurize that system to 600 pounds, that fitting's coming loose really quickly.
And this has happened. I've talked to techs that have said they've forget. It's actually funny because the reason they bring it up is because they'll say that they'll get up to like 400 psi and everything's holding, and then all of a sudden the press fitting will blow off the pipe, and they're like, oh shit, we forgot to press that one. Well, that's your mistake. You know
Yeah.
what I mean? Like, you need to, if you're gonna fit pipe together, you gotta, like, I've fit pipe together and went and pressure tested it and go, oh my god, I forgot to braze that one fitting over there, right? It's the
Yep.
same thing with anything. You have to, when you're doing your job, I mean, if you're going to be standing in front of a bunch of fittings, before you go pressurize, make sure everything is sealed properly. Make sure it's either pressed or it's brazed in properly. Because imagine the same thing with if you're doing a VRF system and you're putting in a branch line for later and you put a cap on, same thing's going to happen. That cap's going to blow right across the room if you go up to 600 psi,
Oh,
right?
yeah. And, think about it. Okay, so let's say you're doing this in an occupied building, and you've got piping that goes through part of the building that's occupied, and that cap comes off, or that fitting comes loose above a ceiling in an occupied classroom, and hits some kid in the classroom, or hits the teacher. The lawsuit that's going to come about from that, you don't have deep enough pockets. I don't have
Yeah.
deep enough pockets. When you get ready to pressure test your system, and I think this is the big thing, is getting people to understand, when you're going to pressure test a system, you need, before you put the first ounce of increased pressure in that piping system, have a plan. Everybody out there, every company out there should have a standard operating procedure for how to pressure test a system. And it should be a written procedure. The reason I say that,
I can guarantee you 99% of companies out there won't have that
I
written plan.
I won't argue that, but what I'm saying is, and okay, so I'm going to put my forensic hat on for a few minutes. When I look at how people do business and how people do their jobs, if you have a written procedure and you say, this is the way we are going to do, how we're going to pressure test a piping system, these are all the steps we're going to go through from beginning to end. Yep. What you're doing is, one, you're establishing a company policy. Two, God forbid something happens. An employee gets hurt, a bystander gets hurt, whatever. The first thing you're going to be able to do is go, yes, we followed the procedure, or no, we didn't. It's all about liability and risk avoidance, and understanding what that risk avoidance looks like. Mm-hmm. I mean, at the end of the day, whether we like it or not, the world is full of lawyers, and we've got to be able to deal with that fact. Is we're dealing with lawyers, insurance companies. In the U.S., we're dealing with OSHA. I forget what the Canadian Safety Council is.
Well, I deal with WMIS.
Yeah. So I mean,
workplace hazard, and I can't remember all the
yeah,
what all the letters mean at this point in time.
But at the end of the day, if something happens on the job site and you've got this procedure all written out and everybody's following it, it makes life much easier, because now you can say, look, this is what we have to do. We want to be a safe company. And in order to maintain our safety record, this is what you have to do on site when you're pressure testing. You know, what happens if you're pressure testing a piping system with compressed air, water, nitrogen, whatever, and somebody that has no idea what you're doing or what's going on walks into the mechanical room at about the same time a fitting blows loose? If you've done your due diligence and you've had a defined procedure, let's say you've put up caution tape. Now, doesn't mean you don't enter the room. It just means that, hey, look, we've got a procedure going on in this room right now that could be dangerous. All of us that are in the room, we understand the hazards. Well, the poor electrician that walks into the room and has no idea about pressure test and piping walks into the room and a fitting blows off. One, he's liable to have to go change his shorts. But two, what happens if he gets hit by a pipe fitting flying across the room? Even if it's only a 3/4 inch 90, guess what? It hurt,
Yeah,
So,
but I see what you're saying. If that procedure's in place, you've put the tape up, you put any signs up, and he walks in, now he's the one that's liable because he's walked across that barrier.
right.
Right.
And at least he walks in with the knowledge of what's going on. Doesn't mean he can't go in the room. It just means, okay, hey, these guys are pressure testing piping systems. I need to be aware of it. The electricians do it all the time. When they energize panel boards, they put big signs up that the panel board's now hot, right? Well, why we as refrigeration guys, as pipe fitters, as service mechanics, shouldn't we be providing the same warnings? Because the last time I checked, if I pressurize a piping system, I can't see what's going on. We talked about leaks. That one of the reasons hydrostatic testing is better than pneumatic testing is if I put water in the piping system and I got a leak, man, it's really easy to see. I can see the leak.
Yeah.
Pneumatically, last time I checked, I can't see air. We know it's all around us, but I can't see it. That's why we use soap bubbles when we're leak testing a refrigeration system, right? Because we can't see the leak. Now, if it's been in operation, we may see the oil traces, but that doesn't necessarily tell us where the leak actually is. It just tells us, hey, there's a fitting that's leaking, or a Schrader that's leaking. It doesn't tell us whereabouts on the circumference of that fitting that the leak actually is.
Yeah. It's just a sign that a leak exists in the general area.
Right. And this is also the reason that if you're going, like we talked on a refrigeration system, you're going to test with nitrogen, raising it up gradually, is you're trying to prevent that massive blowout. The last thing you want to do is have a fitting blow loose above a ceiling someplace because you forgot to braze it or you forgot to press it, because it'll scare the jeebers out of everybody in the building. So if you test and bring pressures up slowly, now you got a greater chance of finding it before it blows apart.
Yes.
And it's really about, and if you've got all this stuff detailed in a procedure manual, and it doesn't have to be, you don't have to have 15 pages of stuff. It could be a 1-page document that just says, look, this is our procedure for pressure testing. And if you make a company policy that says, hey, look, for water piping systems, as long as it's normal hydronic piping, we're always going to test with water because it's safer and it's easier to identify leaks and find them, then that's what the policy is. And I think it's just getting everybody to think about what's the right thing to do and how to protect yourself, everybody you work with, and everybody on the job site, and your reputation.
Yeah. No, I get it, and I'm sure probably some of the larger multi-trade companies that do this kind of stuff on a regular basis probably have a procedure in place. But I've never heard of anybody having one in place in HVAC for pressure testing, refrigeration systems. Probably because a lot of that stuff is in the manual, the install manual. Like for instance, Mitsubishi, their manual tells you to go up in increments, and it tells you what the maximum pressure you should be pressurizing at. But doing it in increments is in their instructions, right?
Yeah, and it may very well be. So you create an SOP, or standard operating procedure. Maybe part of the SOP is always follow the manufacturer's testing instructions.
Mm-hmm.
It could be that simple.
Yeah. Yeah.
And companies spend an inordinate amount of money developing employee handbooks, but do they cover all the stuff that talks about, pressure testing and installation and defining procedures for those things. And I think it depends a lot on the size of the company. You're a relatively small company, so you got ultimate control over what's going on.
Yeah, it's
If
only
you
me.
got Yeah, if you had 10 or 15 people working for you, now maybe you'd want to create a manual that says, okay, look, this is how we're going to do things, because you want better control over what's going on, and you want to make sure that
Yeah,
all the guys you got working for you are doing what you want them to do.
and I think that opens up another that opens up another rabbit hole that could be talked about at another point. But when you have everything, okay, I have my brazing manual, like this is how I want my employees to braze. I have my pressure testing manual. This is how I want my employees to troubleshoot. If you have all this written out and they've signed it saying, okay, yeah, when we get hired, these are the manuals, read them, sign them. This is how we want you to do things. If something goes wrong on a job site and they're liable for that, it's hard to fire someone nowadays in any industry, I think, because
Right.
there's so many pushback. But if you have these manuals written out and you can say, hey, listen, this guy or this girl, whoever it is, they've been a pain in my butt employee since I hired them. I put these manuals in place, and I've discovered on 3 different occasions they've skipped instructions. They didn't follow it. I said, now I have more of a case to get rid of this bad employee without having any lashback on my company. So those manuals could come in handy for that too.
Right. Well, and that brings up a good point. I
It's a whole
know.
other rabbit hole,
Oh yeah.
really.
The reality is most states and most jurisdictions are at will from an employment standpoint. However, you fire somebody because of, and I don't mean to pick on the lawyers, but I'm going to pick on the lawyers. There's so many of them out there that will take a case on contingency that, hey, look, I'm going to sue this company for you for 40% of whatever you get out of them.
Yeah.
And people will go, okay, because it doesn't cost them anything.
Yes.
And now all of a sudden you're getting sued because you fired Billy Joe Jim Bob because he didn't do his job correctly. But he says, well, I did exactly what I was trained to do. And you have nothing to back up how you trained him or what
That's right.
procedure you laid out. Those
That's right.
manuals will protect you to a certain degree from those frivolous lawsuits.
Yeah.
Because now you hand it back to the lawyer and say, well, he signed this paper that says this is the procedure I'm going to follow for brazing or pressure testing or driving my
and
truck or
and and
whatever.
and I will say it's funny. It was in the U.S. those types of lawyers. There's way more of them, and because in Canada we don't sue as much as you guys do in the U.S.
Right.
When I was in Vegas, I saw a billboard that made me laugh. It was like hurt in slip in a hotel or hurt in a hotel, and call this guy, and it was like that's hilarious
Yeah.
because there's lawyers in Vegas. If you slip and fall in a hotel, they're right on that to sue that hotel, right?
Oh
So
yeah. It's funny here in the U.S. Lawyers advertise. The personal injury lawyers they're all over the place. My son, who lives in Dayton, was driving his car. Lady ran a light, broadsided him, wrecked his car, all that kind of neat stuff. In 3 days of the accident, he had no less than a dozen letters from ambulance chasing attorneys going, oh, we'll represent you. We'll sue the party that damaged your vehicle. My son's going, I wasn't even hurt. What's the big deal? Why are you sending all
yeah,
this crap to me? And this is the way some of these people work.
it reminds me of the character Saul Goodman. You ever watch Breaking Bad?
No.
No, okay, all right. Everybody that's listening to this, if they've seen Breaking Bad, Saul Goodman is like he's a lawyer in the show, and
Mm-hmm.
he's sort of like a dirty type lawyer that works with different criminals, and he's the type of guy that would go after an injury like that. Because it's funny because I think it's supposed to be like an exaggerated version of a lawyer that's an ambulance chaser almost, because
Okay.
when in the scene, if you go into his like waiting room, there's all kinds of people. There's people with like collars around their neck and stuff. It's just,
Okay.
it reminds me of Saul Goodman. Anyway, people that have watched the show can relate to that.
Yeah. So, in kind of bringing this all back around to where we started, understanding that, when you compress air, this is the other thing to think about. In our environment, the normal environment is about 20% oxygen in our normal breathing air. As soon as you start to compress it, what happens is that percentage starts to change a little bit, and you now concentrate it into a much more dense pocket. And under the right conditions, you can actually create a hazardous mixture that's explosive, not just in stored energy, but because of the high oxygen concentration, it can actually become dangerous. And so you really have to kind of think about what you're doing, what material you're using. Now, refrigeration is not so much a big deal because nobody uses compressed air to pressure test the piping system. We're going to use
Well, they
dry
shouldn't
nitrogen.
be, but I bet you there's people out there that do it.
Oh, I'm sure there are. I've always used either dry nitrogen or CO2 just because, one, they're relatively inexpensive. I know they're clean and dry, and I don't have to worry about them. But I'm sure there are guys that do. And I'm not saying that using compressed air is the wrong thing to do. Let's say I've hydronic coil in an air handler or in a fan coil, and I've repaired a leak on the coil. It froze up and I had to braze the tube ends or something like that and get the coil back in operation. I don't have any nitrogen, but I got an air compressor. Yeah, I'm going to test that coil with air. Now, does it mean I'm going to take it to 200 psig? Probably not. I'm going to take it to 10 or 15 or 20 psig. But I'm also testing a very small component part. So, if we think about this, and this is to give you an idea of testing procedures. So manufacturers, when they build a coil and they go to test that coil, they pressure test it with air. Okay, they're not using nitrogen. They're going to test it with air. However, the two connections to the coil, they're going to seal them up and connect. One is connected to a hose, and they put it in a tank of water and then pressure test it with air. Well, it does two things. One, if you get it in a tank of water and there's an air leak, guess what? You find it really quickly, right?
Yep.
Two, if something happens and a copper tube ruptures, guess what? It ruptures underwater. Shrapnel doesn't go very far because the water dampens it. It slows it down considerably. I don't know if you've ever seen ballistic testing for a gun, but when they want to get the bullet to get the striations off the bullet and save the bullet, they shoot it off into a tank of water. Because guess what? The water absorbs all the energy.
Yeah.
Pressure cylinders for nitrogen, CO2, propane, self-contained breathing apparatus, scuba tanks, all that. Did you know when they test those fire extinguishers also? Did you know when they test those, they test them underwater? Because they test them with air, but they put them in a tank underwater, but it's buried 15, 20 feet deep and it's full of water. Well, guess what? If the tank explodes, if it fails the pressure, radically fails the pressure test, guess what? It's not hurting anybody.
Yeah.
It explodes in the tank of water, makes a loud noise, maybe blows some water out of the lid, but doesn't hurt anybody. And there's no shrapnel, at least not in the air, not airborne anyway. It's all in the bottom of the tank.
That's why all the superheroes in the movies, they always take the bombs that are about to explode and drop them in the ocean.
So, at the end of the day, when you're out there pressure testing a system, think about what you're doing. Think about the hazards. We kind of tend to take it for granted because pressure testing's a bit of a benign. 99% of the time you pressure test it, it's not a big deal. Everything goes off without a hitch and you move on, right? Be aware of your surroundings. Be aware of what you're doing. Take your time. Avoid using air, compressed air, and because of the entrained energy that's in that compressed airstream. And be very careful. What I don't want to see, I don't want to ever see anybody I know name in the front page of the newspaper or on the front headlines of the news that they were injured on a job site because they got hurt doing their job. I
Yeah.
never want to see that.
Yeah.
That
Me
is
neither.
the absolute worst thing that can ever happen. Because everybody out there, whether I know you or not, we're all brothers and sisters in this industry, and we all support each other. Hence the reason you keep doing podcasts.
We should all support each other for sure. There's people out there that don't like to get on the support bandwagon, but we should all and all act as a community. But
Right.
that's for a different topic. But Tony, this has been enlightening, and I mean, I hope young apprentices and younger or even people that are new to HVAC for a second career have listened to this and taken away that pressure testing can be dangerous. And like we just gotta make sure we're doing our due diligence, making sure the piping's sealed before we pressure test. In applications where water can be used, that might be safer. And let's use those increments when we go up in any pressure test. I guess whether it be water or compressed gas, right?
Right. Well, and let's make sure, that the seasoned guys out there are properly training the younger folks and passing on all of this knowledge. There's a lot of things that don't necessarily get taught in the schools the way they should be. Let's make sure we're
Mm-hmm.
teaching everybody and making sure we are all working safe together.
Yep. On that note, Tony, thank you very much. I appreciate the time today, man.
Hey, thank you, sir. Thank you for having me. As always, it's been fun.